logs to solve problems that, like real life problems that are actually something that occurs. So it's just showing you where a log can be used outside of the math classroom. One of those has to do with pH. You guys found pH in your science classes, right? You know what that is, measures the acidity of a solution. So it's found by doing a negative log of H3O+. H3O+ represents what's referred to as the hydronium ion concentration. So this formula is on there. You don't have to memorize it. If I were to ask you a question about this on the test, I would give you the pH formula. I just want you to be able to use it. So here is an example. Part A. Find the pH of a solution with a hydronium ion concentration 2.5 times 10 to the negative 4. So the pH formula that I just gave you, pH is a negative log, and then in parentheses you do your 2.5 times 10 to the negative 4. So if we just plug that in, I get a pH of 3.6025. We usually just go to one decimal place for pH, so just your pH is 3.6. Second question is find the hydronium ion concentration if the pH is 7.1. So we're using the same formula, but I flipped what I gave you. So if you plug that in for your pH, that means 7.1 equals a negative log of the H3O+. And what could you do with that negative? Now let's just divide it over. So a negative 7.1 equals log H3O+. Then what would we have to do to get that by itself? Since there's only a log on one side, we go to exponential form. So 10 to the negative 7.1 is equal to that. So if we type that in, you are not going to get a pretty answer on these. It'll be in scientific notation. So when I type in 10 to the negative 7.1, I get 7.94, a bunch of decimal places, then it says E negative 8. So what that means is 7.94 times 10 to the negative 8 power. So that's a couple of examples with pH. Just solving those log equations. Either you just get to plug it in and put it in your calculator, or you have to manipulate the equation first. Are there questions on either of those? Second place where it's used a lot is exponential growth and decay. This function, A of t just means the amount present at time t, is equal to a sub 0, meaning your beginning amount, e to the kt power. If that k is a positive number, that means you will have growth. So as time goes on, you're going to have more of it. If k is negative, that means it will be exponential decay. As time goes on, we will have less. All right, so I wanted to look at a couple examples involving exponential growth and decay. All right, if 800 grams of a radioactive substance are present initially, and 2.5 years later only 400 grams remain, how much of the substance will be present after 4 years? Okay, we're talking about exponential growth or decay. Is this one growing or decaying? Decaying. There's less over time. So here is our general formula. Okay, A sub 0 is our beginning amount. Do I know my A sub 0 here? Okay. K is a constant. Did I tell you what that constant was? No, but I gave you the information to find it. I know that after 2.5 years, I have 400 grams remaining. So, what would my A of t be? My amount present at time t. 400 equals, my beginning amount was 800. E, I don't know K, but what's my T? Okay, so what we're going to do is plug this in so we can find that missing K value. So if I wanted to solve this, what would we do first? Divide by the 800. So 400 over 800 is 0.5 equals E to the 2.5K. Then what? Add a natural log. So I get the natural log of 0.5. What happens if you have a natural log and an E? Cancel. Equals 2.5K. So we can divide by 2.5.
Something went wrong. Please try again.
Sorry.
So if we put this in our calculator, natural log 0.5 divided by 2.5, our constant is a negative, which we already knew it would be negative because it's exponential decay here, 0.2773. Okay, so what this tells me is that overall, my general equation here is 800 e to the negative 0.2773 t. We had our beginning amount, we have our constant. So now we can find out how much remains at any given point in time. Specifically, I asked you how much was present after 4 years, so we just have to plug in our 4. So we can just plug all that in our calculator. And we would expect to have even less present after this time, right? It's decaying, so as time goes on, we'll have less and less. And I get 263.86 grams remaining. I thought maybe we should do another one of those just to make sure we were okay with it. You guys want to try it on your own first? Take a second and see how far you. So we have 600 grams are present initially, so that's your A sub 0. After 3 years, 300 grams remain. Sometimes that 3 years is referred to as the half-life. It's just how long does it take until you have half of what you started with. So if we plug this stuff in, my amount is 300 equals my beginning amount, 600. E to the k times t, which was 3 here. So if you divide, you get 0.5 equals e to the 3k. Add our natural log. A natural log and an e would cancel. So divide by 3. And so your k is a negative 0.2310. Did you guys get that part? So now my equation, we know our actual formula then is 600 e to the negative 0.231 t. So the amount after 6 years, you just plug in your 6. And you get 150.04 grams. Any questions on exponential growth rate? One more scenario where we are going to use logs at times would be talking about interest problems. Now we've done interest before. The formulas are on the front of your handout in case you've forgotten them. That's your compound interest and your continuous interest. So that part isn't new. Well, let's take a look at this question. How long will it take for the money in an account that is compounded continuously at 5.75% to double? So continuous interest, that's your A equals PE to the RT. What's the 5.75? That's our rate, 0.0575. Okay, I just said I want it to double. Did I tell you how much you started with? No, so pick an amount. Let's say we started with 5, 10, 2, any of those will work. Then how much would you end with? 10, or whatever you put in for your P, just double it for your A. Okay, we are trying to find how long, so we are solving for the T this time. So my A is 10 equals 5 E to the 0.0575 T. So what would you do? Divide by 5, and then regardless of what you had for your A and P, that should be at 2. Okay, can I get a common base here? No. Since it's an E, we can add a natural log on each side. We know a natural log and an E cancel, so we have the natural log of 2 equals 0.0575 T. So divide. My time turns out to be 12.05 years. So just slightly over 12 years until we double our investment. Did everybody get that? One more of these. How long will it take $1,000 invested at 2% interest, compounded quarterly, to grow to $2,700? So which interest formula am I using? The first one, your regular compound interest. So what's the 1,000? T is what we have today, our starting amount, our principal. 2%, so my rate is 0.02. Compounded quarterly, so that means n equals 4. To grow 2, so my final amount is 2,700. So plug in. We have to solve for t. So what do we do first? So we get 2.7 equals, let's just go ahead and simplify that. What is 1.02, or 1 plus 0.02 divided by 4? Okay. Now what do I have to do? Trying to get to my t. Can we get a common base? No, so then we add a log. Does it matter what kind of log here? No, there's no benefit because it's not going to cancel. Okay, so we have the log of 2.7 equals, that exponent comes down, 4t log of 1.005. So now you can divide by the 4 log 1.005. Make sure you put that entire denominator in parentheses when you plug it in. We get 49.787 years. Okay, we've done these interest problems before. It was just you never had to solve for your t before. You were usually solving for the rate or something like that where we didn't need logs to do it. So I'm just switching what we're solving for, so in order to do that we need a log. Any questions about this? So the last thing I want to talk about. We know that in general, if I want to evaluate a log using my calculator, we have log 10 and we have natural log buttons on our calculator. Now, I know some of you have probably already figured out how to get logs of different bases on your calculator. But if you want to change bases, there is actually a formula to do that. For instance, if I asked you to find log base 2 of 7, do you know 2 to what power equals 7? No. So if we were trying to find that, we could set it equal to x. We could change it to exponential form. And then what would you have to do? Add a log. And we would choose to go with probably like a log base 10 or a natural log because those are the buttons that we have access to on our calculator. So your x comes down. And then to get x by itself, you would end up dividing. So we can take any log that's given and change it to whatever base we want by doing the log of the argument divided by the log of the current base. Now here is my requirement. There are ways to do any log. I know you can go into the math menu and you can do log base 2 of 7 on your calculator, okay? On these problems, I will say work required for credit. Because if I started throwing variables in here all of a sudden, your calculator would be worthless to you. And if you don't know this change of base formula, then you would be in trouble. So we aren't going to do anything too crazy with it. I'm just going to probably put a question on the test asking you to evaluate one of these, and I'll say using the change of base formula, and then I'll say work required for credit. So you have to write out what you are plugging in your calculator.
Do we have to write all that, or can we just?
No.
si-
What you will have,
Simplify down to just like x equals log 7 and log 5.
yes, all we'll have to do is this. What I did right here was prove why the change of base formula works. So from now on, if I want to do a problem, all I have to do is the formula. So if I asked you to find log base 5 of 7. Okay, you could set it equal to x and go through that whole process that I just did. But if you remember your formula, it's just the log of the argument divided by log of the base. You could also choose to do natural log of the argument divided by the natural log of the base. You will get the same answer both ways. So that's the work. You have to write one of those down. And then we divide them. I said 4 decimal places, so you get 1.2091. And last one, what would I write down? Alright. Is this okay with everybody? So that's my lesson for today. And now we are officially done with everything in chapter 4. So, third part of the day, talking about what you guys need to do. Yesterday, I posted a 4.5 handout. And I told you you needed to do 9 through 16. Today, I have posted a 4.4 and 4.6 handout in Classroom. Both of these are due at the end of class tomorrow. Okay, that means you should be working on them, and you've got time right now to work on it. But if you really get stuck on one, you'll have time to ask me about it tomorrow. Okay, so both of those will be turned in at the end of class. Also, quite a few of you will not be here on Friday, which is when we are supposed to have our test. So I am also going to give out the Chapter 4 study guide. That is due on test day. So if you are taking the test Friday with me, then it's due Friday. If you have to take the test Thursday, then you need to have your study guide done Thursday. Tomorrow will be a work day. Thursday will be a class review day for those of you that don't have to go ahead and take it. And if you do need to take it early, then we'll do it on Thursday during class. Does that